Hi everyone! Today I'm going to be talking about a really cool phenomenon that most of you have probably seen at some point. Once I was playing around with water and oil, and I realized that if you have a cup of fresh water and you put an oil drop in it, nothing really seems to happen. But the cool part comes in when you put another oil drop in the cup. Notice that the two drops seem to be attracted to one another and they eventually combine. After some research, I realized that this has a name, and it's called the hydrophobic effect. Hydro referring to water and phobic referring to fear. Oil is a hydrophobic or water-fearing molecule, and water on the other hand is a polar molecule. Polar molecules have a partial negative charge on one side and a partial positive charge on the other side. Salt, for example, dissolves in water because the partial positive charge on the hydrogen in water is attracted to the negative charge on the chlorine in the salt, and the partial negative charge of oxygen in the water is attracted to the positive sodium in the salt. These attractions are the reason why salt dissolves in water. Now, these attractions do not happen to nonpolar things, such as oil in this case, because nonpolar things don't have any charge, so water doesn't really have anything to be attracted to. According to my biology textbook, the hydrophobic effect states that when two nonpolar molecules are put in water, they tend to congregate. But why? They're not charged, right? So why do they seem to be attracted to one another somehow? The book does not delve into why they tend to behave this way, so after some research, I learned that this behavior is due to a physics concept known as entropy. In simple terms, entropy means randomness, disorder, or chaos, and a rule in physics states that the universe is always moving towards disorder. Another question, why? Why is the universe doing that? This might seem very intuitive, but it could be very difficult to understand. But let's think about it in terms of probability. There is always a higher chance for things to be in one of the infinite disordered states than in one of the very few ordered ones. An example is when you eat something, you're transforming all the highly ordered macromolecules, such as carbohydrates, lipids, and proteins, and breaking them down into less ordered ones, such as glucose, triglycerides, and amino acids. Now let's say you go on a walk. You're transforming the energy that you have obtained from those broken macromolecules into mechanical energy, and some of it will even be lost as heat. That's entropy. Now, what does this have to do with the hydrophobic effect? Well, when the first oil drop was put in water, water molecules started surrounding it. When the other drop was put, water molecules surrounded the second one too. What's the big deal? Well, this decreased the entropy of the system because there was a very high concentration of water in the nonpolar regions relative to anywhere else in the cup. To prevent this, the oil drops move towards one another, thus reducing the surface area around them, which allows less room for water to surround the oil, achieving higher entropy. Believe it or not, many biological processes rely on the hydrophobic effect, which in a way is the result of entropy. One of those biological structures is the cell membrane. The phospholipid bilayer is structured the way it is because of the hydrophobic effect, which wouldn't be a thing really without entropy.